Lecture G4, Temperature and Humidity. This is the lecture about water influencing our building. What is influencing our building? That's a fact, we all know that. It's driving rain, vapor, splash water, surface water, black water, capillary water from groundwater getting into our building, and we need to deal with it. We need to decide for this impacts. We are aware of water being a fluid. We are aware of water being boiled to gas. That's what we do when we boil water. We put energy into the water, and this latent energy, latent heat, which is brought into this energy, which is transferred into latent heat, changes the distance of the molecules within the water, and that generates the gas. And with this gas, the water and the gas, the fluid water and the gas, we have to deal in our facade construction. We do talk about water absorption in a water absorption coefficient with different materials. When we look at this solid brick versus a solid sand lime brick, it's obvious that the solid brick is a lot more porous, allows a lot more water to be absorbed versus a solid sand lime brick. Same counts for concrete and cellular concrete. Cellular concrete being a lot more porous, allowing a lot more water to be absorbed. Gypsum takes a lot of water, and then the plasters are kind of reasonable, and then the polymers, that's the paint, they obviously have to be quite resistant to absorb water. We are used to this by the so-called water vapor diffusion resistant factor, and air is defined as 1. Metal is infinite, so there's no water diffusion in metal, and that's why it's an infinite resistant. Bitumen is quite well. Insulation, not that perfect. Concrete, bit better, but not that perfect either, depending on the material. The range is related to the different types of insulation, for example. And this diffusion resistance is defined in the so-called SD value. The diffusion resistance of a component layer is described by the water vapor diffusion equivalent air layer thickness. That means an air layer of, for example, 1,500 meter is called watertight. An air layer of less than 1,500 meter is kind of, there's a diffusion happening. And an air layer of 0.5 meter is actually an open layer. And with this SD factor, we define different materials and their resistance against water. Next aspect we have to talk about is the mold growth. Mold growth happens if there's a certain humidity and a certain temperature reached. The one sample they show here is a surface temperature of 20 degrees, which when we design our facade outside -5, inside whatever, 25 for example in this sample, then we have a surface temperature of 20 degrees and a constant humidity of 80 degrees, mold growth happens. Well, that's quite humid. So the critical parameter which we always tackle as engineering task is 50% of air humidity with a critical temperature at the surface of the facade of 12.6 degrees. We can have that in a different graph like this one. You see the temperatures, the inside and the outside temperatures. You see the water vapor and the humidity. And for example, in a 20 degree room with a 50% humidity, this 50% means 8.6 gram, which is not a lot, and a dew point of 9.2. So we need to engineer that this dew point is never reached, so that there's no mold growth at the inside. And what does that mean for a building? This is this part where we talk about condensation happens, humidity below dew point. This is exactly this point, so condensation happens here. Other parameters which we need to take care of to deal with moisture, it's rising humidity from the soil. So we directly place our solid structure on a soil. There's no barrier in between. Humidity comes from the soil in our system and starts to rise. penetration by driving rain, so rain being forced by wind through the facade and then comes to the inside, especially exposed positions would have this kind of difficulties, and something which we see in arid areas a lot, hygroscopic humidity caused by salt in the stone, in the mortar, and then this hygroscopic humidity creates salt default at the inside of the facade. And by this we go to the different types of constructions, as we always do in this, the single shell construction, where we see moisture penetrating the facade, either being brought at the outside or penetrating the facade, the insulation at the outside, which hopefully is tight enough to allow no moisture getting in, humidity getting into the system, and if there's humidity in the system, it finds its way out of the system. Then the external wall for internal insulation, so outside here, inside there. If there's rain getting into the system, we hopefully get the humidity out of the system, dried out of the system, versus the rear ventilated wall construction. So we have the insulation, we have the ventilation, we have the outer layer, which is the raincoat, and if there's any humidity in the system, hopefully it's drained out of this at the bottom of the main structure. And by this I stop again with the two books which we made and the building physics booklet by Langner, which may also be an interesting one for you to dig into.